Let us start our lecture, and the first topic for today is the law of large numbers for Markov chains. For Markov chains. Okay, let me recall you the usual law of large number. It says that if you have a sequence of independent, identically distributed random variables, such that they have finite first moment, then we know that the averages of xi converges almost surely to the expectation of xi as n tends to infinity. Okay, sometimes this theorem is called the strong law of large numbers for ID random variables. And now let us consider Markov chain. So let xk be a Markov chain on a state space E. Today I will consider E, which is a finite set. So, and I also will assume that all states of E communicate. So all states communicate. And my question is the following. Consider averages of some function of x over n. And the question is, what is the limit? Is there a limit? If yes, then what is this? So if xk are ID, so if you have a trivial Markov chain, then the answer is expectation of x and okay, of x1, say, or x0. But if they are not, then the question is, okay, if it is a constant, then, and if it is an expectation, then what is the starting distribution? What is the distribution? And later we will see that under these conditions, there is a limit, and you have to write here expectation with respect to stationary distribution. Okay. Let us analyze this sum, and then I will formulate the theorem. And at first, let us consider the simplest function f that is equal just indicator. So f of, let's consider f of x is indicator that x is equal to I, where I is a fixed number. The number I. And let me make a picture of trajectory of Markov chain. So assume that this is like random walk. Each unit of time, one step up or one step down. Okay. Let me denote this random variable before the first hitting I by zeta0, this by zeta1, this by zeta2, and so on and so forth. And I will say that this is cycle number 1. This is a cycle number 2, or excursion number 1, excursion number 2, and so on and so forth. It follows from the strong Markov property of Markov chains that this xi1, xi2, xi3 are independent, identically distributed random variables. So psi k greater than or equal to 1 are independent, identically distributed random variables. Xi0 may be different because you start from another point. And the state, we assume that the state space is finite and all states communicate. So probability that all xi's are finite is 1. So this is well-known fact. And also that expectations of zeta is finite. So if you don't know this fact, then prove this. So this is an exercise. By the usual strong of large numbers, we know that averages of zetas converge with probability 1 to expectation of zeta. And now I would like to investigate this sum. So sum k between 1 and n, indicator, or k from 0 to n, that x k is I. So the numbers of visits to I. And okay, let this point is excuse me, so n small and small here, and assume that this is time n, and that this time n belongs to the cycle with the number n capital of n. So what does it mean? So here is random variable zeta of n, and this is n's capital visit to I, and this is n plus n visits of I. So what can we write then? Well, at first, this sum is equal to n of n. And on the one hand, we know that zeta0 plus zeta1 plus zeta2. So at this point, so actually eta n is equal to zeta0 plus zeta1 plus so on plus zeta n minus 1. So this number is eta 1, eta 2, eta 3, and so on. And we have inequalities that n of n, excuse me. So this is eta n, and this number is eta n plus 1. No, this is not true, sorry. This number is zeta 0 plus zeta 1 plus zeta n minus 1, and this number is sum zeta 0 plus zeta 1 plus zeta sub n. So we have inequality n greater than or equal to zeta 0 plus zeta n minus 1 and less than or equal zeta 0 plus zeta with index n. And now let us divide left-hand side and right-hand side by capital N. Capital N, which is capital N of n, it goes to infinity as n small goes to plus infinity. And we have here the following sum. Zeta 0 over n, which goes to 0, plus zeta 1 plus zeta n over n. And we may apply the strong law of large numbers for the right-hand side. Please be careful. Generally speaking, n capital is a random variable, but we know that it goes to infinity with probability 1, so the limit of this is expectation of zeta. Now look at the left-hand side. Multiply the left-hand side and divide by left-hand side by n minus 1. So let me write here n minus 1 over n. And by the same reasoning, the left-hand side converges to expectation of zeta. This converges to 1. So the left-hand side converges with probability 1 to expectation of zeta, right-hand side to the expectation of zeta. So we have the following convergence. Limit as n goes to infinity n over n of n is expectation of zeta with probability 1. And now recall me that n of n is sum of indicators. So if we flip this, then we have the limit. Yes?
Excuse me, can I clarify, please? We have in one circle that n it's the sum of zeta.
Yes.
And it's big number. It's the length.
So n is index such that n belongs to this n cycle. The cycle, so n is a number of cycle.
N big, yes.
N capital yes is the number of cycle that contains n small.
A little bit lower, we write that it's the sum of zeta, but zeta is the length.
Yes. So if n is here, then this point is zeta 0. This point is zeta 0 plus zeta 1. This point is zeta 0 plus zeta 1 plus zeta 2. This point is zeta 1 plus zeta 2 plus so on, zeta with index n capital. Minus 1, sorry. This. Thank you, Igor.
So it's recursive now.
Thank you, Igor. So this point is this. This equality is incorrect. Thank you very much.
Yes, so we take n of n small such that...
Yes, so n is the number such that n small belongs to this interval, such that n small is greater than or equal to this number and less than this number.
Thank you. And
So we may formally write something like this, right? So this is like this.
Yeah. So look at this formula.
Yeah, so this is
So
this
I
formula
have
in
to
the...
write here less than to be very rigorous. But
so this formula in the numerator is the definition of this
yes,
n
this
capital.
is just definition. Yes, exactly. So this formula is just definition of n capital.
yes, now it's clear. Thank you very much.
Yeah, if I make mistake, please don't hesitate to interrupt me. And now flip this ratio. We get the following limit: n capital divided by n is converges to this. By the way, this random variable is this number is positive, and on the other hand, n of n is just sum of indicators. So we proved that excuse me, n small, we proved that the limit of this exists and is equal to this random, the 1 over this random variable, where psi is the length of the cycle. The zeta is time between hitting I when you start from I. So we may write here like this: 1 over expectation, you start from Y, and then consider sigma I, where sigma I is infimum k greater than 0, so k is not 0, such that x k is I. So we have this beautiful formula. On the other hand, the question is how to find this expectation. The answer is yes, we know how to solve it. We have to write down certain system of linear equations and solve them and find this expectation. Well, a little bit later, we will see that this number is closely related with stationary distribution of a random walk. Well, and now let us consider expectation of some k from 0 to n indicator that x k is I over n. Well, expectation of sum is equal to the sum of expectations, so we use linearity. And expectation of indicator is probability. And assume for a while that the Markov chain is aperiodic. For a while, then limit of this. Okay, please tell me what is the limit of this probability S. K if X is a aperiodic Markov chain and all states communicate and there are only finite number of states.
This is pi small or pi I
Yes.
small, where this is stationary.
Yes, that is a stationary distribution. Converges to stationary distribution. And the next question is not the question, but the next fact is the following fact from mathematical analysis. So it's known that if you have sequence of numbers such that xn converges to x, then limit of averages is also x. And now this is xk. This converges to pi as k goes to infinity. So their averages converges as n goes to infinity to pi if Markov chain is aperiodic. Well, if Markov chain is periodic and D is a period, then the proof is almost the same. I leave it to you. Then this limit exists for numbers like 1, d plus 1, 2d plus 1, 3d plus 1, and also 2d plus 2, 2d plus 2 with period d. And if you consider like Markov chain with a period, then you will see that these limits exist because the corresponding sequences n d plus k n greater than equal to 1 are aperiodic Markov chains, and you can do everything like this and obtain limits. And again, the limit will be the unique will be the stationary distribution of the Markov chain, and it's known that stationary distribution is exists and unique under our assumptions, even if we don't assume a periodicity. And now return a little bit back. On one hand, we know that this limit is equal to this, and we know that the limit of expectations is this. So are this limit equal or not? And the answer is yes, because so let me write it once again. Indicator x chi is I over n. So we know that this converges almost surely to 1 over sigma I. And these are non-negative random variables that are less than or equal to, I summed starting from 0, so less than 2. So by Lebesgue dominated convergence theorem, this converges to expectation of this number. So it converges to this number. Hence, we proved the following result. At first, this limit exists almost surely. It equals to this. Moreover, this is related to the stationary distribution. So let me now formulate the result as a theorem. So under our assumptions that finite state space, communication of all steps, that limit as n goes to infinity, number of visits to the state I up to average number of visits up to time n is equal to 1 over average time between two consecutive visits to I and equals to pi almost surely. By the way, how to find the stationary distribution? Игорь, Вадим? What is so the answer, you have to solve system of linear equations. P is P times P, where pi is stationary distribution. So it's, if E is 1, 2, 3, m, then it's vector like this, not column but row, and this is transition probability matrix. And the next question is, okay, other questions about this theorem? Is everything
I
clear?
wanted to clarify, where did we get the expectation, a conditional expectation starting from I? So I lost this this
Because
moment.
what is zeta?
Mhm.
What is zeta? Zeta 1, zeta 2, zeta.
The length of a
So
cycle.
yes, the length of the cycle. So we start from I, we end
Mhm.
at I.
Mhm.
So assume that from the very beginning, Markov chain start from I. So what is zeta? So it's time needed to
Come back to I. Mhm.
return back to I. And we denote this moment by sigma I, the first instant, the instant of heating, the
Mhm.
heating time. And in the definition of heating time, K is greater than 0. So the first time when you return back. Sigma. Here is sigma. Thanks. Not zeta, sigma. So you start from I, you return back.
Yeah, this makes sense. Thank you.
Thanks. And the next question, what is the limit of averages? Some function of the Markov chain. And now let me write f of xk as the following sum. So let me write f of x as sum I in E. So this is finite sum. F of I times indicator that x is I. Then this sum is equal to sum over I, f of I times indicator that xk is I over n. And now let us interchange these sums. And sum k from 0 to n, f of I indicator x K is I over N. And now we see that f of I is independent of K, so we can write it here. And let me write parentheses like this. We know that the limit of this is pi, stationary distribution. So the limit, this limit is equal to sum of f of I times pi. So probability times certain value. So the answer is expectation. If initial distribution is pi, f of x 0. So just value times probability. By the way, we can write here x of 0, x of 1, x of 2. If you start from stationary distribution, then it's x1, x0, x2, and so on have the same distribution. And now let me formulate important theorem that limit of averages f of xk exists almost surely and equals to expectation of f of a Markov chain if initial distribution is the stationary distribution. So we have this law of large numbers. Now let us reflect about conditions of our theorem. What happens if, for example, state space is infinite? We may start from the same picture and these zeta1, zeta2, zeta3, zeta(n), they're independent, identically distributed random variables. Well, if the state I is transient, then delta k may be infinite with positive probability, and you will never return to I. And if I is transient, then it visits only finite amount of times. Then the corresponding limit is 0. If I is recurrent state, then you do all our reasoning and you'll get the same answer that you use the law of large numbers. And it's known that if expectation of zeta is infinite, then the corresponding limit also exists almost surely. But for infinite E, this may be infinite. This is true. Our next theorem about next theorem. This theorem is satisfied with the following remark. If all states communicate and this is finite, then stationary distribution exists and unique, and you have this equality. If this is infinite, then stationary distribution does not exist, and the limit is 0. However, you have to, so it's not immediate consequence. Again, if E is infinite and assume that everything here is finite, then you have to interchange two sums and to write down that the limit of sum is equal to sum of limits. So you have to apply certain limit theorems. Everything is okay is if f is finite, for example. If f is infinite, you have to apply certain result, maybe Fubini theorem. Oh, no, not okay. You have to think about this. And now let me formulate without proof two results. This is theorem 2, this is theorem 3. So if E is finite, all states communicate. Let's consider the following limit of averages. Indicator that xk is I, xk plus 1 is j over n. So what is this? For example, this is state I, this is state j. So this is, so Markov chain is like random walk. You may consider it like a random walk on a graph. And the sum is a number of transitions from I to j that you go through this edge. And the answer is, oh, maybe you may guess the answer. What do you think? Are there any ideas?
Pij.
Okay. Close to the correct answer. N times pi. So at first, you may think like this. You have to visit I, and the frequency is approximately pi, and then to make jump from I to j to multiply by this probability. So this is correct answer. So this is exercise. And the probably the most generalization is this. Limit as n goes to infinity, sum of certain function of xk plus 1 and so on, xk plus m, like m plus 1 consecutive numbers divided by n is equal to expectation given that initial distribution is stationary, function g of x0, x1, xm, almost surely. So this is also exercise. And the proof is similar to the proof of theorem 2 and theorem 1. So you have to consider you have cycles, independent cycles. You have to be careful and to write and then you will see that almost all reasonings work. Okay, questions? Okay, if no, now we start a big section that is called convergence in distributions. Convergence in distribution. So the aim of this course is to prove that if you have random walk or perturbed random walk, and then we scale time and space, then in a limit we will see a Brownian motion, for example, or a Brownian motion with certain perturbation. And the question is, what does it mean that in a limit we see a Brownian motion? I would like to recall you the notion of convergence in distribution, or sometimes we will say weak convergence. And this type of convergence will naturally appear when we study scaling limits of random walks. Okay, let's start with the definition. So let E be a metric space. We introduce Borel sigma algebra. Sigma algebra. And let psi n be a sequence of random elements with values in E. This means that psi n for every n is measurable mapping from omega with certain sigma algebra F to E with Borel sigma algebra. So if E is a real line, then psi n is a random variable. If E is Euclidean space, then psi n is a random vector. If E is R, then a random variable. If E is RD, then we call random vector. We say random vector. If E is a space of function, for example, space of continuous function indexed by t in 0t, then psi is random process, stochastic process. In this case, psi take values in C0t. So in some sense, psi is a function of two variables, t and omega. If omega is fixed, then psi is a function of t is continuous. Sometimes we don't write this index omega and write like psi of t. And the delicate equation is this. So this is exercise assume that psi t is a collection of random variables, is a collection of random variables. So what does it mean? So for each fixed t, psi t is a measurable mapping from omega to r, such that for every omega, the mapping t to psi t of omega is continuous. Prove that psi of t is random element with values c0t. Psi is a random element with values in c0t. And another exercise is assume that psi is a random element with values in c0t. Prove that for every fixed t, psi t is a real valued random variable. So the question is measurability. So here you consider Borel sigma algebra in a space of continuous functions. Here, for each fixed t, you consider random real valued random variable, and we consider Borel sigma algebra on the real line. Well, and now, okay, so these were exercises. Now, the definition of convergence in distribution. Sequence xn converges to random element C0 in distribution if for any continuous and bounded function on the space, on this metric space B, so this is continuous and bounded. We have convergence of expectations. F of psi n is equal to expectation of f of psi 0. Well, since f is continuous, then f of psi n is a random variable because continuous function is measurable, and since f is bounded, this random variable is bounded, so expectation exists, is well defined. Sometimes people say that psi n is sequence xn is weakly convergent to psi 0. Sometimes we use this terminology, and the notation is this: psi n such type of arrow to psi 0. At first, let us discuss relation between convergence in distribution and other types of convergences, like almost surely, convergence in probability, convergence maybe in LP sense, and so on and so forth. And important result is that if you have almost sure or convergence in probability or in LP, then you have convergence in distribution. So in some sense, convergence is in distribution is weak convergence. So it's weaker than all other types. So, okay, lemma. If psi n converges to psi 0 almost surely, or in probability, in LP sense, then xn converges to psi 0 in distribution. And the proof follows from the Lebesgue-dominated convergence theorem. Indeed, psi n converges almost surely to psi 0. F is continuous, so f of psi n converges to f of psi 0 almost surely, since f is continuous. All these random variables are bounded by the same constant. Which is finite because of our assumptions. So the limit of expectations is equal to expectation of a limit by the Lebesgue-dominated convergence theorem. So these and these I leave as the exercise. Well, we know that convergence in LP implies convergence in probability. So this is simple part. And to prove that convergence in probability implies convergence of expectation, there are two steps. The first, you have to prove that if random variables converge in probability and f is continuous, then you have convergence in probability. You have boundedness by the same reasoning. And then you have to recall or to prove that Lebesgue-dominated convergence theorem is true if we consider convergence in probability instead of convergence, or instead of almost sure convergence. And here you may recall Riess lemma, for example. Okay, lemma is proved. The next question is this: how to prove convergence in distribution? Well, if you have almost sure convergence in probability or in LP, then there is no problem. But assume that you have some certain sequence of random variables. Actually, here this expectation depends only on the distribution of psi n. So actually, psi n may be defined on different probability space, and nevertheless you have convergence of expectations. Or, by the way, if psi n are just identically distributed random variables, then you have convergence psi n converge to psi 1 or psi 2 in distribution or psi 3. For example, if they ID. So this is really so this depends only on distribution of Xi(n). And the question of weak convergence is non-trivial even for random variables. So if E is R, or if E is Euclidean space, so theoretically, if you use the brute force, and you have to take every continuous and bounded functions, and then to prove convergence of expectations somehow. Well, fortunately, there are nice, necessary, and sufficient conditions. I hope that you have heard them from in the course of probability. So I just recall important theorem. So assume that E is Euclidean space. Then the following conditions are equivalent. The first, Xi(n) converges to Xi(0) in distribution. The second, limit of the distribution function of Xi(n) is equal to distribution function of the limit for every x such that x is a point of continuity of this function, that x is a point of continuity of the limit distribution function. And the third is convergence of characteristic function. For every theta in Rd, we have convergence of characteristic function of f of Xi(n) of theta converges to, let me write like this, limit n goes to infinity is equal to Xi(0) of theta, where phi theta n of Xi of theta is expectation of the exponent I, this is square root of -1, scalar product of theta and x. So this is scalar product of Xi. Scalar product. And this is square root of -1. And very often it's easy to verify convergence of characteristic function. So you don't have to consider all continuous bounded functions, but only sines and cosines or complex exponents. And this is applied in statistics very often. For example, the central limit theorems and its application and other well-known limits and applications to statistics. We worked with characteristic functions a little bit, so let me recall properties of characteristic functions. of characteristic functions. The first property
There's
is
also one more equivalent statement, right? So we will continue to it after.
Do you mean Portmanteau theorem or Alexandrov theorem?
I mean with like for every open set, for every closed set.
Yes, yes, yes. But this theorem is true in arbitrary metric space. We will
Okay.
discuss this this important theorem a little bit later, and
Okay.
probably next lecture, and also important property that is called Skorokhod representation theorem that says that in some sense convergence in distribution is close to almost sure convergence. You know, in one direction, but the result is in other direction is true in some sense. In some sense. Yes, and regarding to convergence in distribution, I recommend you in metric spaces. I recommend you to read or at least take a look at the book by Billingsley, Convergence of Probability Measures. Convergence of Probability Measures. Actually, there were two editions. They're different, but both of them are good. And well, there is non-trivial intersection, certainly, but for example, Skorokhod representation theorem is formulated and proved in the second edition, but not in the first one. Okay. But now let's discuss properties of characteristic functions. So let me recall you. At first, it value at 0 is 1. Like C is a continuous function. So if you forget these properties, is a continuous function, and moreover, it's uniformly continuous. So I'll either recall or try to prove. The third property is non-negative definite. Like C is okay, positive semi-definite function, or I will say just positive definite. This means the following. For every C1, for every n natural number constant, C1, C2, Cn, complex constants, for every theta 1, theta n in Rd, some j k from 0 to n, c j c k complex conjugate, phi theta j minus theta k is a real number that is non-negative. The important result that sometimes called Bochner theorem states that phi satisfies one and 3 and continues at 0, then phi is a characteristic function. Is a characteristic function. And important property is that if xi has a moment, then characteristic function is differentiable, and relation between moments and derivatives. So let me formulate this theorem in one-dimensional case. For example, if expectation of xi is finite, then characteristic function is differentiable, and moreover, its derivative at 0 is equal to I times expectation of xi. If the second moment is, no, let me formulate this like this. If k's moment is finite, then you have this equality. And other direction, if phi is differentiable to k times, so even number of times, then this moment is finite. This moment is finite, and so the first, second, third, up to k, all moments are finite, and certainly you can calculate them as derivative of characteristic functions. Well, we have just a few minutes, and let me recall you a beautiful proof of the central limit theorem. So I will consider the case D is 1 that states that if psi k are IID, independent, identically distributed random variables, such that their second moment are finite, then we have convergence in distribution of some psi k minus their expectations divided by sigma square root of n, where sigma is variance of xi, to the standard normal distribution. Well, I subtract here the expectation, so without, and divide by variance, so without loss of generality, I will assume that expectation of xi is 0 and variance is 1. So the general case, consider yourself. Then we have to prove this divided by square root of n. And let's calculate characteristic function of this. So characteristic function of this. At first, we know that characteristic function of sum of independent random variables is equal to product of characteristic functions. Or if you forget this property, you may write the definition that e to the power I sum psi k theta over n, and this equal to product of expectations I psi k theta, let me write here, divided by square root of n, and we see that this is characteristic function of psi k at the point theta over square root of n. And now we recall that all psi are independent identically distributions, so this product is equal to characteristic function of psi at the point theta over square root of n to the power n. And we know that psi has, yes, square root of n. Thanks, Vadim. And we know that the second moment is finite. So we may write down Taylor formula for characteristic function, 1 plus derivative of characteristic function at 0 times theta over square root of n plus second derivative at 0 times theta squared over n plus O small of 1 over n to the power n. The first moment is 0, so this is 0. The second moment is equal to minus, so I squared times expectation of psi squared. We assume that this is 1, so this is negative 1. So this expression is equal to 1 minus theta squared over n plus O small of 1 over n to the power n. And now this is just mathematical analysis. The limit is e to the minus theta squared for every real number theta, over 2, excuse me, I forget to write here over 2, so 1/2 of the derivative over 2. And then you say, oh, this is characteristic function of the standard normal distribution. I forget to mention the following very important property, that if two random variables have the same characteristic function, then these random variables have the same distribution. So if we see in a limit normal distribution, then we know that you have convergence to that the distribution is determined uniquely. Okay, that's all for today. Thank you for your attention. Are there any questions or comments? If no, see you next week.
Yeah.
Yep. Have a good day. Goodbye.
Goodbye.
О, Вадим, когда мы с вами встречаемся?
Можем